Okay, here we are, ready to start lesson 1.3, the language of relations and functions. So we're going to start with relations and the definition of a relation. If you have sets A and B, a relation R from A to B is a subset of the set A cross B. So remember, the elements of A cross B would be ordered pairs. And then we define an ordered pair x comma y in A cross B, and we would say that x is related to y by R, which you write x r y, short for x related to y, if and only if the point xy is in R, which is a subset of A cross B. So the set A is called the domain of R, and the set B is called the codomain of R. And the notation for a relation R may be written symbolically as x, r, y. I read that x is related to y. And that means that the point x comma y is in the set R. Remember that being a subset of A cross B. If you put a line through the R, it means not related to, and then thus the point x comma y is not in R. Okay, so that feels a little wordy and complicated. We'll do an example to make it clearer. Okay, we have two sets, A and B. A is just the numbers 1 and 2, and B is a set of numbers 1, 2, and 3. We're going to define a relation R from A to B as follows. Given any xy in A cross B, xy in R, for xy to be in R, that means that x minus y over 2 has to be an integer. Okay, so first we're going to list all the ordered pairs in A cross B. So we did this in our last class. So the ordered pairs in A cross B, you have to take each element of A and pair it with each element of B. So I have 1, 1, 1, 2, and 1, 3. So that's each element of the first element of A paired with each element of B, and then do the second element of A paired with each element of B. Okay, so I have 6 total elements in A cross B. Some of them are also elements of R. Okay, so R is a subset of A cross B, and each point lives in R if and only if you do x minus y and divide by 2 and get an integer. So of these 6 points, which of them satisfy this criteria? So let's just check. We'll write it out for a couple. 1 comma 1. If you do the x coordinate minus the y coordinate over 2, we get 1 minus 1 over 2, which is 0, and that is, in fact, an element of the integers. So 1, 1 is in R. But then if I check, say, 1 comma 2, x minus y would be 1 minus 2 over 2, and I get negative a half, which is not an element of the integers. So 1, 2 is not an element of R. So you have to check each point. Let's see. 1 minus 3 is negative 2 over 2 is negative 1. So this is an integer. So I will just check off underneath. That one was an integer. That one was not. That one's an integer. 1 minus 3 over 2. And then 2 minus 1 over 2 is a half, which is not an integer. 2 minus 2 over 2 is 0, which is an integer. And then 2 minus 3 over 2 is negative a half, which is not an integer. So to list out the points, the ordered pairs in R, we have 1, 1, 1, 3, and 2, 2. Okay, now we're just practicing with a notation. Is 1 related to 3? That's just asking, is 1, 3 in the set? Okay, so those if we go back and look at the definition, x related to y means x comma y is an element of the set R. Okay, so 1 is related to 3 because 1, 3 is in the set. Okay, is 2 related to 3? Well, 2 comma 3 is not in the list of elements of R, so that one's a no. And is 2 related to 2? Yes, because 2 comma 2 is in the list of points in R. What are the domain and codomain of R? So the domain is A from A cross B, and A was 1 comma 2. And the codomain is B from A cross B, which was 1, 2, 3. Okay, for the next example, we're going to define a relation C. So we're using the letter C instead of the letter R this time. It's going to go from R to R, the reals to the reals. And we're going to define it as any xy in R cross R. So you look at all the ordered pairs in R cross R, and then we say the ordered pairs that live in C satisfy this equation, x squared plus y squared equals 1. So we are going to look at some ordered pairs and decide if they live in C, if they are elements of the set C. So 1, 0, is that an element of C? Well, is x squared plus y squared equal to 1? For this x and y, we would have 1 squared plus 0 squared equals 1. Yes. 0, 0. Well, 0 squared plus 0 squared, does that equal 1? No. And then negative a half root 3 over 2. Okay, negative 1/2 squared plus root 3 over 2 squared. Does that equal 1? We get 1/4 plus 3/4, which equals 1, so yes. And now I'm asking, is negative 2 related to 0? This is the same kind of question as up here, but this is asking, is negative 2 comma 0 an element of C? So I use the same procedure. I plug into x squared plus y squared equals 1 and see if it's true. So negative 2 squared plus 0 squared, does that equal 1? No. Is 0 related to negative 1? We plug in x squared plus negative 1 squared. Does that equal 1? Yes. And then 1, 1. So x squared plus y squared. Does that equal 1? No. What are the domain and codomain of C? The domain and codomain always come from right here where it says C goes from R to R. This is the domain, this is the codomain. And then when they write the definition, they'll say elements in a set cross a set. The first element is the domain, the first set is the domain, the second set is the codomain. So in this case, both the domain and the codomain are the real numbers. Okay, we want to draw a graph for C by plotting points that are on C in the Cartesian plane. So we go back and we have a few already, right? I know that 1, 0 is a point on C. Negative a half root 3 over 2 is on there, and 0, negative 1 is on there. So I have 3 points I can start with. So let's see, we had 1, 0. We'll make each tick mark a half. Okay, so I have 1, 0. I have negative a half root 3 over 2, which is about 0.866, so it's like not quite 1. And then we have 0, -1. Also 0, 1, and -1, 0 will satisfy it. And it looks like we are forming a circle. You could plot more points if you weren't sure, but we are making a circle of radius 1. All right, let's suppose R is a relation from a set A to a set B. The arrow diagram for R is obtained by putting all the elements of A into one region as points. We'll represent them as points. And then we put all the elements of B into another region, and we usually put them side by side. So you'll have like a circle here with elements of A in it, a circle here with elements of B in it, and then for each X in A and Y in B, you draw an arrow from X to Y if and only if X comma Y is an element of R or X is related to Y. So you'd have like an X and a Y, and if X is related to Y, you draw an arrow like that. All right, so let's look at an example. We have sets A and B. They both are the set 1, 2, 3, and we're going to define a relation S from A to B so that for every xy in A cross B, xy will be an S if X is less than Y. So let's list out all the elements of A cross B first. So elements of A paired with every element of A paired with every element of B. So I have 1, 1, 1, 2, and 1, 3. The first element of A paired with every element of B. Then second element of A paired with every element of B. And then the third element of A paired with every element of B. Okay, now we're going to list the elements of S by looking at the definition, X is less than Y. For all these elements in A cross B, the subset of them that lives in S are the ones where the X coordinate is smaller than the Y coordinate. So let's just go through and I'll put a little check mark over the ones that satisfy that. That's it. There's 3 of them. So we have 1, 2, 1, 3, and 2, 3. Those are the only 3 points in the list where the X coordinate is smaller than the Y coordinate. So now we draw an arrow diagram for S. This is the set S. Okay, so all the X's from A live in here. All the Y's from B live in here. So A only has 1, 2, and 3 in it. 1, 2, and 3. So we represent those as points, 1, 2, and 3. And then B is also the set 1, 2, and 3. Okay, and then S is how we connect these. Okay, so S goes from A to B, and I will connect points, X coordinates with their corresponding Y coordinates from the set S. So 1 goes to 2 and 1 goes to 3. So I'm going to draw a line from 1 to 2 and from 1 to 3, and then from 2 to 3 for the third point. A function f from a set A to B is just a special kind of relation. It has the domain A, codomain B. It's a special kind of relation that satisfies two extra requirements. Okay, the first one is that for every element in A, there is an element in B such that x comma y is in the relation. So let's go back, look at what we just drew here. 3 is an element in A that does not have an element in B that corresponds to it. So this is not a function. It fails number 1. Okay. Every element x in A, there is an element y in B such that the two are related. So x comma y would have to be in F. Okay, and then the second one, for all elements x in A and y and z in B, if x, y is an element of F, if an ordered pair is an element of F, and so is xz, xy is an element of F and xz is an element of F, then y and z would have to be the same. So that is, for each x, you can't have two different y values. So when I look at this diagram, we failed the second one also because I have 1 comma 2 and 1 comma 3. So for the same one, I've got two different y values. So we fail property 2 as well. We can state them less formally. Every element of A is the first element of an ordered pair in F. That's number 1 here. And no two distinct ordered pairs in F have the same first element. Okay, function notation. If A and B are sets, and F is a function from A to B, then given any element x in A, the unique element in B that is related to x by F is denoted f of x. F parentheses x, we read that f of x. So for example, if A is the set 2, 4, 6 and B is the set 1, 3, 5, which of the relations R, S, and T defined below are functions from A to B? So A. So we have to decide whether or not it's a function. So every element of A has to appear as an x value. So I have 2, 4, and 6. I have x values 2, 4, and 6. Okay, so we've satisfied property 1. Okay, and then property 2 said that any two distinct points cannot have the same x coordinate. Okay, so we have a 4 here and a 4 here, 4, 1 and 4, 3. That makes this not a function, fails property 2. You can't have the same x coordinate going to two different y coordinates. So the problem is those 2 points makes us fail property 2, so it's not a function. This relation is not a function. Okay, for B, for every x comma y in a set A cross B, xy being an S means that y equals x plus 1. Okay, so we're using the same A and B here. So y has to equal x plus 1. So if I use every element of A, so y equals x plus 1. If I plug in the x's from A, then I get y equals 2 plus 1, which is 3. Y equals 4 plus 1, which is 5. And y equals 6 plus 1, which is 7. Now, the problem is that if I try to draw a diagram, A and B, A I would put in 2, 4, and 6, and B I put in 1, 3, and 5. All right, and then according to my calculations here, when I plug in a 2, I get a 3. So I would draw an arrow from 2 to 3. when I plug in 4, I get 5, so I do 4 to 5. And then 6, there's nothing in B that 6 goes to. Okay, so 6 is supposed to go to 7. 7 is not in the codomain, so this is not a function. Because 7 is not an element of B. Okay, now I have an arrow diagram, 2, 4, 6 to 1, 3, 5. And every element in A is connected to something in B. And I don't have 2 lines coming out of any element from A. So 2 goes to 5, 4 goes to 1, and 6 goes to 1. So if I listed these as ordered pairs, I would have 2, 5, 4, 1, and 6, 1. Okay, so every element of A, 1, 2, 4, 6, appears as a first coordinate. And then I don't have any of my elements of A appearing as a first coordinate twice. So this is a function. FCN I use to abbreviate function a lot. Okay, so in terms of an arrow diagram, the 2 properties of a function can be stated as there is an arrow coming out of each element of the domain. So we've got that. And no element of the domain has more than 1 arrow coming out of it. So that satisfies properties 1 and 2. Okay, number 11. Let A be the set A and B, and let S be the set of all strings over A. We're going to define a relation L from S to Z non-negative integers, so that for every string S in S, so little s represents a string, in big S, the set of all strings. And for every non-negative integer n, S, n is an element of the relation, means that the length of S is n. So S is a string, n is a number, right? So you input an element from S, the set of all strings, and the output is a non-negative integer. Okay, so these 2 numbers paired together are part of the relation L if the length of S is n. So is AA, BAA, that is a string from the set AB over the set AB, and it has length 5 because there are 5 letters in it. So 1, 2, 3, 4, 5. So we have a string and its length. So that is in L, right? Because the length of the string is 5. But AA, BAA, 7 is not in L because 7 is not the length of the string. All right, let's evaluate L of BBAA, BBAA. We just have to figure out how long it is. 1, 2, 3, 4, 5, 6, 7. So L of that string is 7. L of AAA is 3, the length of the string. Is L a function? Why or why not? So we have to think about the 2 properties. Okay, would every string have a length that we can measure? Yeah. Yes. So property 1 is that every element of the domain gets paired with an element of the codomain. So in this case, we're asking, does every string have a length? And yes, every string has a length. It's just the number of letters in it. Okay. And then the second one is that you can't have 2 strings, 2 inputs with different outputs. So does every string have a unique length? You can't have 2 different lengths. And the answer is yes. Every string has a unique length. one and only one number can describe the length of a string. So this is yes. We've satisfied both properties of a function. So L is a function. Okay, the last thing I want to talk about is one more useful way to think of a function. It's a special kind of relation, and we can think of it as a machine. So elements of the domain go into the machine, and the machine does some changes or processing of the input, and out comes f of x, the output, an element of the codomain. So for example, a simple function is the squaring function. It goes from the reals to the reals. So you input real numbers and you output real numbers. And we're going to define it by the formula f of x equals x squared. So you put in x's and out come x squareds. So just as a little practice, evaluate f of 3. That would be 3 squared, right? You put a 3 in, turn the crank, out comes 3 squared, and you get 9. If f and g are both functions from a set A to a set B, f equals g if and only if f of x equals g of x for all x's in the domain A. For example, we have two functions f and g that go from the reals to the reals by the following formulas. F of x equals absolute value of x, and g of x equals the square root of x squared. So we can check a couple of numbers. These two have to give the same output when you put it the same in, if you put in the same x into f and into g, you have to get the same output every single time for every single x value you plug in. So I'm going to do a couple just to demonstrate, and then we'll decide if this is always true. So let's do, say, f of 3. That would be the absolute value of 3, which is 3. And then g of 3 better give us 3, or we can, if you find one time that they're not the same, then we say f does not equal g. So g of 3 would be the square root of 3 squared, which is the square root of 9, which is 3. Okay, so it matches for this one x value. We better check some negatives because absolute value function and squaring functions both have things that happen with negative numbers. So let's do f of negative 3. That would be the absolute value of negative 3, which is 3. And g of negative 3 would be the square root of negative 3 squared, which is the square root of 9, which is 3. So yeah, I'm pretty convinced that this will always be the absolute value of x. Okay. So yes, f equals g.